Right guys, here is a little practical video just to show you a little practical demonstration of how potential dividers are used in the real world. Okay, basic setup, we've got 200 ohm resistors in series with each other. Let's just check our V in first. So our total supply voltage, we're looking at about 5 volts, so 4.96 volts. Okay, right. V1, which is the voltage across R1, and V2, which is the voltage across V2. Not surprisingly, the voltage is shared, okay? But we have a 100 ohm resistor as R1 and a 270 ohm resistor as R2. Not surprisingly, the 270 ohm resistor gets the bigger share of the voltage, almost, give or take, 3 times the voltage, because we've got almost 3 times the resistance. Okay, right, now the actual practical use of potential dividers doesn't involve 2 fixed resistors, because that's not really that useful, is it? Just having a fixed voltage. It becomes much more useful when we introduce one of the resistors that can vary. Now what do we got here? We have a variable resistor. Now as you can see here, we have the voltage across the variable resistor, the voltage across the fixed resistor. Now just by changing the resistance of the variable resistor, we can change the voltage across it. But more importantly, we can also change at the same time the voltage across the fixed resistor. So, low voltage means low resistance. If we turn the resistance up, the voltage will go up. But at the same time, the voltage across R1 goes down, because V1 plus V2 has to equal VT. Okay? Now, even better would be to have a variable resistor that can vary automatically. Okay, I'll go back to that. Let's go back to the variable resistor. Right, how do we use the variable resistor? How do we use the potential difference across it as a V out? Well, basically, we take the potential difference across the variable resistor and we can put a component there as our load. Now the load, this is the thing we are powering with our variable potential difference. So as we can see here, the resistance is high, so the potential difference is high. So if the potential difference is high, we get a high current. And as we can see, the LED is bright. Now if we take the resistance down, the potential difference across the variable resistor will go down. If the potential difference across the resistor and the diode goes down, because remember, the potential difference here is the same as the potential difference here. So if we take the resistance down, the voltage across here will decrease, and as we can see, the LED gets dimmer, all because the voltage across here is going down. So that's how you take your load. Similarly, if we wanted to put the load here instead, we would get the opposite, wouldn't we? So now we have low resistance here, so low potential difference here. But if there's a low potential difference here, that means that there's a high potential difference here. Now if there's a high potential difference across the 100 ohm resistor, there's a high potential difference across the LED. If there's a high potential difference across the LED, we get a big current and it's bright. Now, if we turn the resistance up, the voltage goes up. This gets a bigger share of the voltage. This gets a smaller share of the voltage, and as if by magic, the LED goes down. Okay? Exactly how dimmer switches work in the house. Right, this is what I was going to do before. Variable resistor. Even more useful would be another type of variable resistor, but one whose resistance varies automatically. Okay? No prizes for guessing that this one is an LDR. Okay, a light-dependent resistor. A resistor whose resistance changes depending on how much light is falling. Now, at the moment, we have bright conditions, and if we put our thumb over it, we get dark conditions. Now, not a great change there. Not a great change there, because any guesses? Well done. The LDR has a very large resistance in bright conditions and dark conditions, so having a 100 ohm resistor is not going to make that much difference. However, if we were to swap the 100 ohm with a 2.2 kilo ohm, now we have, because that value there, 2,200 ohms, is in the same ballpark as the LDR. So now we get quite a difference between bright conditions and dark. Now remember, for an LDR, a light dependent resistor, when there's lots of light hitting, the resistance is low. Remember, it is the opposite, isn't it? Low light, high resistance. High resistance, high potential difference. Lots of light, low resistance, therefore smaller voltage. Okay. Now, finally, to use the V, to use this potential difference, just like we did with the variable resistor, we take our load component. This is going to be our V out, our output voltage, and we simply connect it across in parallel, that's the important bit, in parallel with the LDR. Now let's just run through this. We have lots of light, meaning low resistance. If there's a low resistance, there's a low potential difference. If there's a low potential difference, there's not much current flowing. Now if we make it dark, if we cover up the LDR, remember, no light means high resistance. High resistance means high potential difference. High potential difference means bigger current. So as we can see, if we cover it up, the LED gets brighter. Okay, I'll just turn the lights off. We can see that a lot more if we turn the lights off. Actually, not much at all, can we? Because when there's lights are off, there's not a lot of light hitting. So there you go. If we were to get a torch and shine it. If we were to get a torch and shine it, then that would, there's the torch by the way. If we were to get a torch and shine it, as you can see, the LED goes off completely. Okay, now very, very useful circuit that, because that's a circuit that can turn something on or off when the light conditions change. Where would you see that before? Have a little think about that. Now, one last thing before I give you this activity to do. One last thing is this circuit turns on a light when it gets dark. Okay, if we want a circuit that turns on a light when it's light, we do this. We simply put the LED across the fixed resistor. Because remember, when this goes down, the voltage across this goes down, the voltage across this goes up. Now, as you can see, bright conditions, bright LED. Dark conditions, LED goes off. Make sense? And finally, we can even swap the LED, the LDR rather, with another automatic resistor, the thermistor. Okay. Now that, if we heated it up or cooled it down, would be able to turn the LED off or on.